Okay, so the plan for today is simply to continue on with Chapter 10, Parametric Equations, and likely wrap that up on in Monday's class. Just a reminder that the midterm exam is this week. We've discussed the details of this before, but the main thing I strongly recommend planning to take it on or before tomorrow night if you haven't already done so. It is open through Sunday at 11:59 p.m. But again, there are no due date extensions on the exam, so make sure to leave yourself plenty of buffer so that, if anything goes wrong, a tech issue, a personal issue, whatever it may be, you have plenty of time to get it worked out, find other options, whatever it may be, to reach out to me, let me know anything like that. So um, I think that is all I really have to say on the midterm exam. We've discussed it a couple of times previously. The quote of the day today is a quote by Captain Jean-Luc Picard from Star Trek Next Generation, played by the legend Patrick Stewart. And I think this was from season one, where, obviously Star Trek, they are going about the galaxy and they visit different planets and so on. And they land on this, or not land, but they visit this planet where basically one of their crew members gets into a bit of a jam and they're trying to kind of negotiate for their release essentially. Uh, and the quote is, there can be no justice so long as laws are absolute. Even life itself is an exercise in exceptions. So I saw somebody post this recently on Facebook and thought that it was a good quote. I had seen the episode, but I kind of forgot about the quote. So uh, this actually kind of touches on a lot of really challenging related ideas in philosophy. If you want to kind of an interesting diversion, Google the trolley problem, or you might have heard of this. It's kind of an interesting philosophical dilemma because you state the trolley problem as it is. People will pick an answer and they're usually pretty confident about their answer. They're like, yeah, this is what I think is the right thing to do in this situation. And then if you kind of rephrase the situation and just like with a minor reskin in a sense, then a lot of times people will change their mind. And it's not as clear of an idea as we might think. And really what it touches on is this idea of deontology versus consequentialism. And philosophy professors will probably, roast me for this, but I kind of think of deontology and consequentialism as being two sides of us, or two extremes of a spectrum. There's kind of the by the book way of thinking, which, tends to be like most of us like math and STEM kind of people. We tend to like rules and you follow the rules and the rule is the rule is the rule, period, end of story. Versus somebody who leans more on the consequentialism side may say, well, let's look at the effects of the rule and, what are the ends and can the ends sometimes justify the means? So maybe I kind of, stereotype that side of things as kind of like the lawyers, right? Who say, well, the rule says this, but there are multiple interpretations and we would debate about it in court and you have your perspective, I have my perspective, and so on. And really, I think what a lot of this comes down to is what's kind of your definition of justice? It's not an easy word to define. So some ideas to think about that are related to this, um, but yeah, so famous quote by Jean-Luc Picard in Star Trek. All right, so continuing on with chapter 10. Last time we looked at and graphed this set of parametric equations, and we came up with a cycloid. And as kind of an exercise I gave to you to maybe take a look at this situation. I kind of mentioned how it's like the path that if you had a wheel rolling along the ground without slipping and you put a light at the very edge of the wheel, it's the path that would be traced out by that light. And I said, maybe think about trying to derive this as an exercise. And that's what we're going to do now. It's actually not too difficult to do. So let's consider that we have an X and a Y axis, and this is 0, 0. And we have a wheel, in this case of radius 1, with its kind of bottom point, its point of tangency with the x-axis is touching at 0, 0. And let's say that the wheel is going to be rolling this way, kind of off to the right. So a little bit of time later, or a little bit of rotation later, our wheel has moved over to this position. And now if I look at, say this, let me do this in red, show up. If I look at this line here, like the center point, the center of the circle, down straight to the origin, as the wheel has rolled, this kind of vertical line where the at the end where the maybe LED or something is flashing that we're tracking along, it has now uh, kind of rotated around, right? We have this angle theta. It looks like it's maybe a little bit too short for how far I drew it over here, but you can imagine that this wheel has rolled a little bit without slipping, and the center point has moved to the right a bit. So what about this point here, which we'll call x comma y? Well, let's analyze its x position and its y position separately. So for its x position, well, the center of the wheel has moved from x equals 0 over to the right a little bit. How far has it moved? Well, it's moved linearly left to right the same distance as the little chunk of circumference uh, that it has kind of used up along the circle here. But the circumference of a circular segment is, or the arc length of a circular segment is just r times theta, but my radius is 1. Let me put that in here. So this distance is actually just theta. This arc length is just the distance theta. And that's how much like the spoke or the axle of the wheel has moved to the right when I rotate it through angle theta. The axle of the wheel has moved to the right, but as the axle has moved to the right, the the bottom part of the tire gets left behind a little bit, right? As I'm rotating to the right, in this case, uh, the angle increasing pushes the the light a little bit further to the left. So my light hasn't quite gone theta units all the way to the right. So what is this distance here? The distance from the axle back to the light. Well, there we have our hypotenuse of length 1, and we have a horizontal and a vertical side. And I know this angle up here is angle theta. Note that the angle is kind of on the top right, so things are maybe a little bit wonky from how we're used to seeing sines and cosines. But if I think of this as like, I don't know, what can I call it? I don't want to call it R, I'll just call it A. I see that the sine of theta is opposite A of hypotenuse 1. Sine theta equals A over 1. Or actually, A is just sine theta. And I might as well, while I'm here, note that the height is going to be cos theta of this triangle. So actually, we had our axle move to the right theta units, but then kind of the LED, because the wheel is rotating about that axle, got left behind. It's kind of pushed to the left sine theta units. So what is x of theta? It's theta minus sine theta. And then what is y? Well, I'm kind of running out of colors here, but we know that if we have a circle of radius 1, this axle is at height 1. So this is like height 1, and then minus the vertical distance that my light is below the axle, or it's like 1 minus cos theta. And so not a super difficult derivation as long as we just kind of set up our triangle the correct way. All right, so that is the cycloid. The cycloid also, as kind of a side note, has an interesting property that if you have, say, 2 points, and you're looking between these 2 points, the shortest distance between 2 points is a straight line. But what if I was thinking of rolling a ball down a ramp like this? What's the path between these 2 points that would give me the shortest time from point A to point B? It's actually not a straight line, because we can kind of see that because we imagine that if I had a pretty sharp drop here, this ball is just rolling under the influence of gravity, that's all. If I had a pretty sharp drop here and then did basically a straight line, I really haven't added much distance at all, but this sharp drop lets the ball pick up a lot more speed initially, and it's going to be going a much faster speed for essentially the same distance. So we see that, intuitively, I don't think a straight line is going to be the answer here. And it actually turns out that the answer is a piece of a cycloid, a little, so our cycloid kind of looked like this. Take a chunk of it, flip it upside down, and that's the answer to this so-called brachistochrone problem. Brachy meaning short and chronos meaning time. So the shortest time, brachistochrone problem, the answer is a cycloid. And actually, interestingly, it's also the solution to the tautochrone problem. Tautos meaning something like equivalent, like a tautology means two things that mean the same thing. In fact, if I start the ball anywhere along this curve, it'll take the same amount of time to get to the end. So whether I start here or here or here or here, it gets to point B at the same time. That seems very strange until you realize, wait, well, if I start closer to point A, let's say, further to the left, I've added more length, but on the other hand, I've also added more slope, right? So my ball is going to get going faster initially, and that's going to exactly make up for the added length. That extra speed that it gets from that steeper slope is going to exactly offset the addition of the length, provided that I use a cycloid. Or if I move over to the right, I have a shorter distance to travel, but I didn't get to use this steeper slope to accelerate and get going faster. So I'm going slower, but over a short distance, and those two exactly counteract one another. So kind of interesting little note about the cycloid. Not only is it useful for, tracking lights flashing at the end of bicycle tires, which we probably aren't all that interested in doing, but it's the solution to some interesting problems like these, which arguably we might also not be interested in doing. Okay, so that is the cycloid. And that wraps up our discussion of just kind of the basic introduction to parametric equations, parametric functions. So we are going to move on to 10.2, calculus with parametric curves. Okay, so suppose we have y equals y of t and x equals x of t. We can imagine this being represented by some curve in 2D space. And one of the nice things about parametric functions is that we're not restricted to just kind of functions y in terms of x. We can do all kinds of crazy curves in space, and we don't really have a problem here. But we might ask ourselves, well, if I want to do calculus with parametric curves, I mean, I guess I could pretty obviously do like, dy dt or dx dt, provided y and x are nice enough. But have I lost an understanding of what, say, dy dx means? Have I lost this geometric and calculus interpretation of the rectangular coordinate system, just like x related to y? And the answer is not really, right? What does dy dx mean? Well, it means that if I pick a point on the line, on the curve, if I can find a tangent line, it's just the slope of that tangent line. If I tell you what t we're at, maybe this is t equals 3, you should be able to locate the point that we're at on the curve, draw a tangent line. I mean, of course, provided we don't have corners or jumps or anything, provided it's nice enough, draw a tangent line there. And then the slope of that tangent line is dy dx, right? It is the change in y over the change in x. So it still should make sense to talk about dy dx, even if we have this parameter t, and even if our relationship overall is not y as a function of x, right? It fails the vertical line test. But derivatives these are local properties. So failing the vertical line test over here, I shouldn't really care about that when I'm just looking at this point. Okay, so it seems like it means basically the same thing that I meant before. It seems like intuitively we really haven't, lost or just thrown out this whole idea of calculus and derivatives and things like that. How do we find it? Well, I mean, I suppose one cheating way to do it would be to say eliminate the parameter right y in terms of x and take the derivative. I suppose we could do that, but we saw that often that's not feasible. So how do I find it more directly using y of t and x of t? Well, here I realize that dy dx is just dy dt divided by dx dt. And this is essentially just the chain rule, right? dy dx times dx dt equals dy by dt. It's essentially just the chain rule, right? Uh, so y is a function of t kind of implicitly through f, or sorry, through x. So we can just treat it like a chain rule and then divide to get our answer. So dy dx is just dy dt over dx dt, dy dt being the derivative of y with respect to t. Let me write this a little more explicitly, y prime of t over dx dt x prime of t. So dy dt is a derivative, dx dt is a derivative. We find those two, and then we take their ratio by dividing them. Okay, what about the second derivative? We might be tempted to do something like y double prime over x double prime or something like that, but let's be a little more careful. Remember that dy by dt is dy dt or y prime of t, that's a function of t, over x prime of t, which is also a function of t. This is actually a function of t. Or, sorry, dy dx. dy dx is a function of t. If I want to take its second derivative, I want to differentiate a function of t, but with respect to x. I actually basically just do the same thing I did up here. I take d by dt of the thing I want to differentiate, dy by dx over dx dt. Okay, so let's take a look at this set of parametric equations here. Let's think about it for a minute, maybe draw a graph, and find some information about the derivatives. So I have x of t equals -3 cosine of t, y of t equals 2 sine of t. This feels like it's going to be a circle or something like a circle because of the cosine and the sine. Can I draw a graph of this? I guess I could use the calculator, but maybe for a little bit of practice, we'll do eliminating the parameter. I see I have a cosine of t and a sine of t. Everywhere that I see a t, it's inside a cosine or sine. So I'm looking to use Pythagorean identity somehow. So I note that cosine of t is what? Negative x over 3. And sine of t is y over 2. This says that cos squared t plus sine squared t on one hand is 1 by Pythagorean identity. But on the other hand, from these two equations is x squared over 9 plus y squared over 4. And this I recognize as the equation for an ellipse. So I see that when x is plus or minus 3, I get 9 over 9, I get 1 plus something non-negative equals 1, then y's got to be 0. So my x-intercepts are at plus or minus 3, 0, and my y-intercepts at plus or minus 2, and that forces x to be 0. So that's my ellipse. Let's go a little further with this. And we know that cosine and sine are 2 pi periodic, so we should trace this out exactly once for t in 0 to 2 pi. T in 0 to 2 pi should be one trace of this. But let's figure out where we locate it at on this graph at t equals 0, maybe at pi, and which direction are we going? So at t equals 0, well, x of 0 is negative 3, cos of 0 is 1, times negative 3 is negative 3, y of 0 is 0. So we're at negative 3 comma 0. We're actually over here at t equals 0. And then as t increases just a little bit, if it's just a little bit positive, having trouble getting everything on the screen here, but if t is just a little bit positive, then sine of t is just a little bit positive. So then positive 2 times sine of t is just a little bit positive. Y is just a little bit positive. And of course, x is going to be a little bigger than negative 3. Cosine of t is going to be a little less than 1, which means that when I multiply it by negative 3, it's going to be a little bigger than negative 3. So we were heading this way. So we're starting at negative 3 comma 0, x comma y, and we're progressing around in the clockwise direction. And we probably guess at t equals pi, we should be on the right side. And we see that y is going to be 0 when t equals pi, and x is going to be negative 3 times negative 1, or positive 3 at t equals pi. And then we're back where we started as soon as we hit 2 pi. Okay, so we got a pretty good idea of what's going on now. And now we want to compute derivatives. Let's compute a couple of first derivatives. And to do that, maybe I'm actually going to come off to the right here. I think I have some more room over here I could use. So let's compute dy dx as a function of t, and then kind of apply that to answer these two questions. So dy dx is dy dt over dx dt, or dy dt is 2 cosine of t over dx dt is negative 3 times negative sine t, or 3 sine t. Or this is 2 over 3 tangent t. So this is what dy dx is, function of t. All right, so when t equals 2 pi over 3, let's see, 2 pi over 3, that's 360 degrees over 3, that's 120 degrees. So that is like over here, something like this. So this should be a positive slope, I think, if my picture is, oh, I wasn't being careful. 120 degrees from where we started, which is over to the right. We started at 0 and going to the right. So this is my 2 pi over 3 or 120 degrees. So used to going, from the positive x-axis, it just becomes a habit, but we have to be careful here. So my slope should be negative, actually. Okay, so what is tangent of 2 pi over 3? So let me come over here. What is tangent of 120 degrees? So now I'm in, just to be clear, I'm just looking at what's tangent of 120 degrees. So now I'm kind of like normal trig mode, not this, strange different parameterization mode. So over here, I'm looking for tangent of 120 degrees. And I see that that puts me in the second quadrant, 120 degrees, with a 60-degree anterior angle. So I have a 30, 60, 90 triangle. If my hypotenuse is 1, if my hypotenuse is 2, opposite my 30 is 1, and then square root of 3. So I know that this is a 1, 2, root 3 triangle. And tangent of 120 is going to be like tangent of 60. So tangent is opposite over adjacent as root 3. So tangent is going to be y over x. But here, because I'm in the second quadrant, my x should be negative 1. So this should be negative root 3. So what is dy dx when t equals 2 pi over 3? It should be negative root 3. So in other words, the slope of this tangent line should be negative square root of 3. We do get a negative tangent, a negative slope for the tangent line, so that does seem in line with what we'd expect from this picture. A little bit hard to tell whether the slope should, the slope should be steeper than, say, -1, but my picture is not super accurate. So looks like from the picture, the slope might look a little bit shallower than that, but that's just me not being good at graphing ellipses or being really careful about my gradations on my axes. But we do see a negative slope, and that's what we expect. Okay, so I could ask a different question. I could ask, what is dy dx when x comma y equals 0 comma 2, when x is 0 and y equals 2? So I'm at this point. Well, looking at the picture, I think that this should be a horizontal tangent. I think the derivative should be 0. So how can we approach this? Well, let's see. When x and y are 0 comma 2, that means x equals 0 and y equals 2. Well, if x is 0, that has a couple different solutions, but y equals 2 only has one solution. Y equals 2 says that, well, sine of t has to be 1, and sine is 1 at pi over 2. To be clear, t equals pi over 2. does t equals pi over 2 mesh with x being 0? Yeah, that works as well. Cos of pi over 2 is 0, so that works. So t equals pi over 2 has to be the t input that we're looking for. And what do I see here? I see that cos of pi over 2 is 0, and sine of pi over 2 is 1. So I see my ratio dy dt over dx dt is 0 over 3 or 0. If I try to plug in tangent of pi over 2 down here, when I put the cosine underneath the sine in the denominator, that kind of feels like infinity. It's kind of like a 2 over infinity kind of situation. So, plugging t equals pi over 2 directly into this simplified form at the end here, maybe I should have put a little note here like t not equal to pi over 2 or 3 pi over 2. But we can refer back to the situation before we did that simplification and see clearly that dy dt is 0, dx dt is non-zero, so the ratio then is 0. And we do get a horizontal tangent line with slope 0. So this checks out as well. And now let's compute the second derivative and evaluate when this curve should be concave up versus concave down. I think it should be concave down for t's between 0 and pi, and concave up for pi to 2 pi. That's what it looks like from the graph. Let's see if we get that from the derivative. So for my second derivative of y with respect to x, I want to take d by dt of dy dx divided by dx dt. So I want to take d by dt of the function dy dx, but that's 2 over 3 tangent t, or maybe I'll write it as 2 cos t over 3 sine t. I don't know how much that matters, but let's just do 2/3 tangent t to the minus 1, and then divided by dx dt. What was dx dt? It was 3 sine t. I haven't worked this out in advance, so I think this should work fine. But if you did the, cosine over sine, and use the quotient rule, it should work fine as well. So if I differentiate this, I get negative stuff to the negative 2. Times the derivative of tangent, which is secant squared, over 3 sine t. And let's simplify all of this a bit. This gives me negative 2 over 3. The tangent t goes on the bottom, which puts sine squared t on the bottom and cos squared t on the top. So I got that, I've got that. I need another 3 sine t on the bottom. And then my secant squared t puts a cos squared t on the bottom. So let me make sure I got all of that flipping over the divided by line right. Yeah, I think all of that looks right. My cosine squareds go away, and I get negative 2 over 3 sine cubed t. And I see that for t in 0 to pi, I suppose, let's say open 0 to pi, sine is going to be strictly positive, multiplied by a negative 2/3. So our second derivative is going to be negative. We're concave down. And for t between pi and 2 pi, there my sine will be negative. My sine cubed will be negative. Multiplied by a negative is going to give me positive. Positive second derivative of y with respect to x means we're going to be concave up. And that's exactly what we expected from the picture. Any questions on any of this? Okay, let's go back to our projectile motion example and compute our first and second derivatives of y with respect to x. Now here, remember that v naught and h naught are constants, but also actually theta is a constant. Theta is just the angle that we shoot the projectile at the beginning. So t is the variable. And again, we're looking for dy dx, which is just the ratio of dy dt to dx dt. Dy dt is negative 32 t plus v naught sine theta. And we're dividing that by dx dt, v naught cos theta. Or we can see that this is negative 32 over v naught cos theta times t plus, well, that's v naught tan theta. This is dy by dx, and it's a function of t. So if I say where I am in terms of t, then this tells me what the slope of my arc here is. If this is t equals 1, then it tells me what is this slope dy dx. What about the second derivative? So remember, what we do is we differentiate the first derivative with t, and divide by dx dt. So for the numerator, I take what I just boxed there, differentiate that with respect to t. That gives me negative 32 over v naught cos theta. Remember that theta is just a constant. The v naught tan theta is a constant, it differentiates off. And dx dt is v naught cos theta. Or my second derivative is just negative 32 over v naught squared cos squared theta. Right, so there's my first and second derivatives, y in terms of x. Any questions on that? One little side note, I suppose, is keep in mind this is the second derivative of y in terms of x. And this projectile is actually traveling in 2 spatial dimensions over time. Sometimes we just think of like throwing a ball directly straight up and down into the air. So it's really only a 1-dimensional problem. And then we'll choose to kind of represent, say this is h. We'll choose to represent like h as a function of t, and it might also follow a parabolic arc. But note the difference here. This h as a function of t is a 1 spatial dimensional problem where we're representing the time dimension horizontally. Over here, we're representing 2 spatial dimensions, x and y, and the time component is kind of implicit in tracing out the graph. So note that y double prime of t, the second derivative of y, the height, with respect to t, is indeed just negative 32. Just acceleration due to gravity, right? But the second derivative of y, this 1 space variable with respect to x, the other space variable isn't just that negative 32. It's not just like that gravitational constant. So we might have got here and you might have said, wait, like, is there something else that's accelerating stuff here? We're dealing with something other than gravity? Well, no, because this is the influence from gravity, looking at the height as a function of time. This is something having to do with the concavity of this curve that the actual cannonball or whatever traces out in two spatial dimensions, with time as kind of an implicit thing that's tracing that graph out. So just note the difference there. So it's not like we have some modified form of gravity or something that we're working with. This is just our gravitational acceleration, the same old gravitational acceleration that we're all used to. But this d squared y dx squared is saying something different. It's not the second time derivative, it's the second like spatial derivative. Okay, any questions so far? All right, so this is about where the supplement picks up, the supplemental video. And then I'm going to kind of do a quick recap of that material. Like I said, the supplemental video unfortunately kind of like split us at a wonky place. So just a quick recap of that, and then we'll talk a little bit about polar curves and maybe start areas and polar coordinates. So I think most of this should be review for most of you, but if it's not, take a look back at the supplement and then maybe come back and rewatch this recording. But polar versus rectangular coordinates, we have our good old XY rectangular Cartesian coordinate system. And we can represent a point in this plane as x comma y. And by that, I mean, start at the origin, point yourself in the positive x direction and walk so many units in that direction. If your x coordinate's negative, then walk backwards in the negative direction for x. Turn and point yourself in the positive y direction and walk yourself in that direction with a y coordinate number of units. And again, if y is negative, then walk down instead of up. So we can get from the origin to this point by walking x units horizontally, y units vertically. But another way that we could think about getting from the origin to this point is to say, stand at the origin, rotate yourself around until you're facing in the direction where you can see this point, and then start walking in that direction. Say, for instance, you turned counterclockwise the direction theta from the positive x-axis, and then you keep walking until you get to this point, and maybe you have to walk a distance r to get to this point that where you want to end up at. So there are actually kind of two different ways we could describe a point in this two-dimensional plane. We could describe it as x comma y in our rectangular coordinates, or we could describe it in polar coordinates. Rotate theta units from the positive x-axis and then walk forwards r distance. And a little bit of trig shows the relationship between x, y, r, and theta is that x equals r cos theta and y equals r sine theta. We can kind of think of these as like parametric relationships. So maybe I really ought to get rid of the theta here. Well, now it's not being cooperative, but I got a little too much into parametric equations mode. Really shouldn't be an x of theta. It kind of in a sense is, but x equals r cos theta, y equals r sine theta. And then we can see that eliminating the parameter r squared, eliminating the parameter theta, r squared is just x squared plus y squared. And taking the ratio gives us that tan theta is y over x. So if I know r and theta and want to recover x and y, I use this version, plug r and theta into the right side and get x and y out. Or if I know x and y and want to recover r and theta, I use this version. And I do have to do a little bit, take a little bit of care with the tan theta equals y over x when I invert that, It's not just theta equals arctan y over x. I have to make sure I put it in the correct quadrant and all that as well. But typically we will use r's or radii that are non-negative and thetas between 0 and 2 pi, although that's not a hard and fast constraint. So for example, a polar curve or polar function could be a relationship. Well, a general function is, we think it was a relationship between x and y, between our two Cartesian variables. A polar function could just be a relationship between the two polar variables, r and theta. So instead of like y equals f of x, we could have r equals f of theta. I could say, when you're pointing in this direction to be on this function, you should go this distance. When you're pointing in a different direction, you should go a different distance. This is a functional relationship as long as for each theta, I only give you one r, at most one r. So if we look, for example, at r equals 2 theta, well, so here's my x-axis and y-axis. So theta always is measured going from our positive x-axis when we're in polar coordinates. Well, when theta is 0, r is 0. So when I'm pointing directly in line with the positive x-axis, I go nowhere. So I just start at the origin. When theta increases a little bit, then I'm going to walk a little bit in that direction. When theta increases a little more, I'm going to walk a little more in that direction. When theta increases even more, I'm going to walk a little further. The larger the theta is, the further I walk in that direction. So this is a spiral. It's going to look like this. And we could graph this on a calculator. Let me bring that up here. And so on our calculator, again, if we go to our y equals menu from last time, we had graphed some parametric equations, but r equals 2 theta isn't really a parametric equation. We might somehow be able to force the issue, but it's more natural to go into mode. And instead of function or parametric, we're going to go over one more and choose POL, polar. Now, if I go back to my y equals window, I see that I have r equals. Let me clear this one out as well. So I have r equals, and then I want to put my function of theta in here. So I just have 2, and then my general variable button. X was for my just functional relationships. T was for my parametric, theta for my polar. So if I just hit my general variable button, it pops a theta in there for me. For my window, maybe I'll let theta go from 0, maybe actually all the way out to 4 pi. I'll take my theta step to just be whatever it gives me, so around 0.1 or so. X min, I know that my radii are going to go up to 2 times 4 pi, or 8 pi. And that can kind of be in any direction. So maybe I'll go from minus 8 pi to 8 pi, and maybe I'll just type in 25 on x, and negative 25. Oh, it didn't like that. So we'll do negative 25. I think I hit the minus sign on my keypad and I put in a minus instead of a negative, up to 25 for y max. So we'll just basically use negative 25 to 25 on both axes. And then if I graph, I can see it plot this out. So there's one run around, and then it goes around again. And there's our nice little spiral. All right, so that was, again, a very quick recap of what's in the supplement, but we're going to continue on from here. Okay, so we can ask then in a situation like this, we have this spiral. And again, if I just pluck out a particular point on here that's maybe associated with a specific value of theta, I should be able to look at this point. And again, as long as my curve is nice and smooth and so on, draw a tangent line there and get a slope delta y, delta x. I should be able to take a derivative here. Doesn't seem like there's any reason that I couldn't take a derivative of y with respect to x, even though things are kind of in this r theta scheme. What does dy dx look like? Well, here, if I have r equals f of theta, I can think of theta uh, as the parameter, right? Theta evolving over time, so to speak, or theta evolving from some number to another number is what's tracing out this graph in the xy plane. So really, I can just think of this as though y is just a function of theta and x is a function of theta. Well, why is that? Well, because x is r times cosine of theta, but r is given by f of theta, and same with y. So my xy point is really just a function of theta. If you tell me what theta is, I can tell you what xy point you're at. So dy dx should just be dy d theta over dx d theta because we're just treating theta like a parameter now, parameter just in a parametric equation. Then I say, well, what's dy d theta? Well, y equals r sine theta, but r equals f of theta. So I have y equals f of theta times sine theta, and I want to differentiate that with respect to theta. Differentiate the first gives me f prime of theta times sine theta, and then plus differentiate the second, f of theta times derivative of sine theta is cos theta. And I do something similar for dx d theta, letting x be f of theta cos theta, differentiate, use the product rule, and I get that as the denominator. So let's take a look at this polar curve, r equals sine theta, for theta between 0 and pi. Let's graph it on the calculator first. So I want sine theta. My window, well, my radius can only ever get as big as 1. So here I want to let theta go from 0 to pi. And x min should probably be -1, and x max +1, y min -1, and y max +1. That should get everything on the screen just fine. And there we go. We can actually go ahead and zoom square just to get a little better perspective. Zoom and then hit 5. And actually it's actually just a circle that's centered at like 0, 1/2 and has a radius of 1/2. That was not very circular. I know when theta is 0, when I'm lined up with the positive x-axis, I go 0. So I start here at theta equals 0. No, actually, when theta is pi, I'm back at 0. So when I'm pointing in the negative x axis direction, I go 0 as well. So when theta is something like what, maybe pi over 2. So if theta is pi over 2, what do I get? Well, sine of pi over 2 is 1. That's when I'm up here. So I see I expect to get horizontal tangents at theta equals 0, pi over 2, and pi. That's what I would expect. Let's see if we get that. Let's compute dy d theta. Well, remember that y is r sine theta, or y is f of theta, sine theta, times sine theta, or y is just sine squared theta. So dy d theta is 2 sine theta cos theta. Or we can use a trig identity and note that this is just not sine squared theta, sine of 2 theta. All right, so uh, sorry, my OneNote is being really wonky at the moment, but we only have a couple minutes left, so I don't want to shut it down and restart it and all of that. Okay, so sine of 2 theta is 2 sine theta cos theta, and we're asking when is this 0? Dy d theta being 0 would be kind of one criterion to get a horizontal tangent, and we would just have to check that dx d theta is not also 0 there. Otherwise, when we take their ratio, strange things would happen. We get a 0 over 0, indeterminate form, all that. So when is sine of 2 theta 0? That's when 2 theta is 0, pi, 2 pi, etc. Or that's when theta is 0, pi over 2, pi, etc. We're only interested in thetas between 0 and pi. So these are the only thetas we're really interested. These are kind of the candidates for horizontal tangents. We also would like to check dx d theta. So x equals r cos theta, or x is sine theta cos theta, or x is 1/2 sine 2 theta, which means dx d theta is cos of 2 theta. Right? Sine of 2 theta differentiates the cos of 2 theta, and then the 2 pops out and gets rid of the 1/2. When is this 0? Well, when this is when 2 theta is pi over 2, 3 pi over 2, 5 pi over 2, etc. Or it's at pi over 4, 3 pi over 4, 5 pi over 4, and so on. So I see that it's not at any of these thetas. So I should have horizontal tangents at theta equals pi over 2, at 0, at theta equals pi, and so on. Because I don't also have dx d theta being 0 there. And alternatively, I've also figured out that dx d theta is 0 when theta is like pi over 4, when I'm going out in this 45-degree line, or 3 pi over 4. In between 0 and pi, those should be the two answers for when I get vertical tangents, when dx d theta is 0, but dy d theta is non-zero. So those are my two vertical tangents. All right. Any questions on any of this? Sorry, my OneNote started being really wonky about 15 minutes ago or so. Let me stop the recording.